Hi everybody, welcome to Unit 4. This unit is still on trigonometry, but we're going to look at acute triangles in this unit. So far what we've been doing has all been using right-angled triangles. So sine is the opposite over the hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent, but all of that only works in right-angled triangles. So what happens when your triangles aren't right-angled? And so that's what we're going to look at in this unit. So you can see this in this example. We've got a surveyor's trying to determine the width of a river. So what we're trying to do is determine what this distance is right here. She takes several measurements as shown in the diagram to the right. So how wide is the river? You can see that this is not a right-angled triangle. This is an obtuse triangle. We can still work with it even though it's not an acute triangle. There are some cases where obtuse triangles are a little bit tricky, but that's not the case in this question. I think that what we should do first is fill in any information that we know for sure to be true. And then after that, what I'm going to get you to do is you to solve it on your own, if you can. So stop the video, solve it, and then you can come back to the video. So we do definitely know that this angle right here has to be 41.5 degrees. So that's 180 minus 107 minus 31.5. It is a triangle, so its angles add up to 180. And I'm going to say drop a perpendicular, also known as an altitude, from this vertex here down to this side. And you can call that H if you want, or A, or whatever you want to call it. And I suggest that there is definitely a way, we'll call this distance here D. There's definitely a way to figure out how long D is if we take this triangle and we divide it up into pieces. So go ahead and try that. And when you're done, you can restart the video. Okay, so I'm going to go through the solution. So we know we have, if we take a look here, there is a right-angled triangle, and I'm trying to find H, which would be the opposite to, this is my reference angle of 31.5 degrees, so this is the opposite, and this is the hypotenuse. And if we go to SOHCAHTOA, that means we're going to use sine. So sine of the angle, we'll call it theta, equals opposite over hypotenuse. So sine of 31.5 degrees equals the opposite, which is h, for height of the triangle, over the hypotenuse, which is 220. Multiplying both sides by 220. We get that h equals 220 sine of 31.5 degrees. And when I put that in my calculator, times sine of 31.5, I get 114.9. And it looks like that's in feet. Okay, so now if we go to, let's use this color. Now, if we go to this triangle here, I suppose that was probably a bad color. We have another right-angled triangle where this 41.5 degrees is our reference angle. Again, the height of that triangle is the opposite, and the length that we're looking for is the hypotenuse. So we're going to use sine again. So sine of an angle equals opposite over hypotenuse, so sine of 41.5 degrees equals the opposite, which we now know to be 114.9, divided by the hypotenuse, which we're calling d. And remember, when the d is in the denominator, you can just interchange these two, so d equals 114.9 divided by the sine of 41.5 degrees. And when I do that, now I still have the old number because this wasn't 114.9 exactly. It was 114.9496842 and so on. I still have that number in my calculator, so I'm just going to divide it by the sine of 41.5, and that gives me 173.5 feet. Okay, so this was not so difficult, just by dropping that perpendicular, dropping that altitude from the vertex down. But we don't want to have to do this all the time. We want to be able to solve these in a different way. And so what we're going to talk about now is what's called the sine law. So the sine law is a rule, or it's kind of an equation that works in all triangles, whether they are right-angled triangles or not. This works in all triangles. Now there is a little bit of trick in some obtuse triangles, but not all, but it works for all acute triangles. So let's take a look at what we did in the last example, but just in kind of a generic manner. So what we did is we dropped a perpendicular down from one of the vertices, and we called that h for the height of the triangle. Now remember that a side, when you label a side, it is the smaller case of the angle of the vertex. So if this is vertex A, this is side little a. If this is vertex B, this is side little b, and if this is vertex C, I don't know why that C is there, should be over here, we have this as side little c. So if we take a look at the triangle on the left, the smaller right angle triangle on the left, we get, so we're looking at angle A, this is the opposite and this is the hypotenuse. So we know that the sine of angle A equals the opposite, which is h, over the hypotenuse, which is c. And from the triangle on the right, if this is my reference angle, again, h is the opposite and A is the hypotenuse, so the sine of angle C is the opposite, which is also the height of the triangle, over A, which is the hypotenuse of the triangle. All right, now I'm going to rearrange this a little bit. I'm going to multiply both sides by c. That'll cancel that out. So then we get that h equals c sine of A. And if I do the same thing in the other equation, multiply both sides by A to get that A out of the denominator, you get that h equals A sine of C. And if you remember from our work on linear systems, we've got two equations and they both equal h. So h equals c sine A and h equals A sine C. So if h equals this, if h equals this and h equals that, then this has to equal that. So then that means that c sine A has to equal A sine C. Now if I divide both sides by C and by A, the C cancels here and the A cancels here, so then I get that the sine of angle A divided by the length of A equals the sine of angle C divided by the length of side C. And it actually, we could do this all over again and we could find that this would also be true, that those two things also equal the sine of angle B divided by side B. So the ratios of the sine of the angles to the side opposite those angles is equal for all pairs of angles and sides. And that's how the sine law works. I'm going to stop this video there and move on.